Welcome to the 15th lecture of our course. In the last class, we had discussed about X-ray fluorescence. Just for continuity sake, I will quickly go through about some properties of the X-rays, what we have discussed earlier only. So, basically X-rays are short wavelength electromagnetic radiations produced by the deceleration of high energy electrons, or by it can also be produced by electronic transitions of the electrons in the inner orbitals of the atoms. So, X-rays have a wavelength range of 10 raised to minus 5 angstrom units to 100 angstroms. Conventional X-ray spectroscopy is largely confined to 0.1 angstroms to 25 angstrom units. So, you can generate the X-rays by bombarding a metal target with a beam of high energy electrons. You can also expose a substance to a primary beam of X-rays to generate secondary beam of X-rays of lower energy. You can use radioactive sources. Some of the radioactive sources continuously emit X-rays like curium during its decay process, and you can also generate X-rays from a synchrotron radiation source. So, the X-ray tube generates both continuum spectra as well as line spectra. Electrons are produced at a heated cathode and accelerated towards a metal anode with a potential difference of about 100 kilovolts, and upon colliding with the anode, part of the energy of the incident beam is converted into X-rays, and the continuum X-ray spectrum exhibits a well defined short wavelength limit, which is characteristic of the applied voltage, but not of that of the chemical element. So, you can see that if you use 50 kV, you will get 0.2, and 40 kV you can get X-rays only starting from about 0.3 kV, etc. These things we have seen in the last class with different applied potentials. So, the continuum radiation results basically from the collisions between the electrons and the atoms of the target. Each collision results in the emission of a photon. The energy of the photon must equal to the loss of the energy when it collides with an electron. So, the number of collisions with decreasing energy may occur for each electron as it bounces from one atom to another atom, and this gives rise to continuum spectrum. So, the maximum photon energy generated corresponds to the instantaneous deceleration of the electron to 0 kinetic energy, that is the basic difference, and the kinetic energy of all the electrons can be expressed as Dionne-Hunt law, that is V E, that is product of the applied potential multiplied by the electronic charge gives you a radiation, X radiation, and the same h mu 0, same notations we use to calculate the wavelength. H mu 0 is nothing but h c by lambda, where h is Planck's constant and c is the velocity of light and a is the lambda is the wavelength. So, the kinetic energy is basically the product. Now, let us learn some more about the X-rays, that is X-ray line spectra result from electronic transitions of the innermost atomic orbitals. They occur in the longer wavelength range of 4 to 6 angstroms. The line spectra occur for all elements having atomic numbers of 12 and above. Below that you do not get line spectra. So, usually atomic numbers having less than 23 show only two lines called as K series and designated as K alpha and K beta. These are of short wavelengths. For continuum, for example, K series for tungsten appears at 0.18 and 0.21 angstroms. So, this is the figure we had shown you in the last class, that there are two lines in this range which are line spectra superimposed on the continuum spectra like this. So, elements having atomic numbers more than 23 show L series, which are also designated as alpha 1 and beta 1. There is a threshold voltage for each element, below which line spectra do not appear. For example, below 50 kV no line spectra is obtained for molybdenum. However, above 70 kV it produces a line spectra. Now, here are some elements and X-ray emission lines for some typical elements. For example, sodium atomic number is 11, alpha 1 occurs at 11.909 and beta 1 occurs at 11.617. You will be surprised to see that we are able to calculate the wavelengths at such accuracy only in the case of X-rays. Similarly, for potassium we have 3.742, 3.454 etc. Above this level, above atomic number 23, we have K alpha as well as L alpha, L beta. So, we get 4 lines maximum. Same is the case with rubidium, cesium, tungsten, uranium etc., where I have listed some of the X-ray lines obtained for these things. Now, mostly has shown that there is a linear relationship between the square root of the frequency for a given K or L line and the atomic number as shown below. For example, C by lambda is equal to A into Z minus sigma whole square, where Z is the atomic weight. And you can see that as the atomic number increases, there is a linear relationship in L alpha 1 as well as in the K alpha line frequency. So, this is a very important property of all the X-rays, and the short wavelength X-ray K series is produced when the high energy electron beam removes an electron from the K orbital. This produces an excited ion which emits a quanta of the radiation as electrons from outermost orbitals come back to the ground state. So, K series lines arise from transitions between the higher energy levels and the K shell. Similarly, L series of lines results when an electron is lost from the second principal quantum level directly or from the transition of an L electron from the K level. Now, this is the partial energy level diagram causing X-ray production. Here I have shown you here alpha 1, alpha 2, beta 1, beta 2 etc. And these are all this series on the left part of this figure is K series and the right part is the L series. They also contain some of the fluorescence lines. So, in this figure you can see that the energy levels that are on the left axis versus abscissa are on the logarithmic scale. So, as the energy level increases, the separation between the lines also becomes less and they become crowded at higher energy levels, at rather lower energy levels, but between K shell and L shell the energy levels are well separated. So, the wavelength of characteristic X-ray emissions are also independent of the chemical element, as the transitions do not involve bonding or non-bonding electrons. For example, the position K alpha line for tungsten or any element, whether is exactly same, whether it is an oxide or whether it is a sulphide or whether it is a pure metal or it could be an organic complex. So, whatever be the chemical state of the atom, the wavelengths of characteristic X-ray are always same. That means, irrespective of the state of the atom, you should be able to determine the element by X-ray spectrum. Now, based on the properties of X-rays, a number of analytical methodologies have been developed, and these are based on the atomic emission, for example, that is known as X-ray emission spectroscopy, XES. And then you can study the emission surface emission, that is known as Xray emission spectroscopy. You can study the X-ray fluorescence spectroscopy, where the emitted X-rays have a wavelength longer than the excitation wavelength, that is X-ray fluorescence spectroscopy. Then you can have electron spectroscopy, that is ESCA. So, here you are studying only the specific portion of the surface of the sample, what elements it contains, etc., using the X-ray line spectrum. And you can also have X-ray absorption spectrometry, that is nothing but you take a sample, pass the X-rays, whatever comes out, the loss in energy of the X-rays can be determined as a function of a known element concentration. So, that is known as X-ray absorption. Another way of using another analytical technique very useful for X-rays is X-ray diffraction. That is, you can study the crystal structure of the substance, where the elements where the atoms are located. So, this you can do, and we are not going into details of each of these techniques, but we are going to concentrate only on the X-ray fluorescence technique, but this much of information is essential before we proceed into the analytical aspects. Now, here I am continuing where I left my last slide, that is what I had described number of analytical techniques like XES, AES, XFS, ESCA, X-ray absorption, etc. The phenomenon that is occurring there, I am trying to show here. Here the X-ray is coming in the top figure A, you can see that radiation is falling and then it gets excited and then it emits the radiation. And B is Xray, the radiation is falling onto the sample, and again depending upon the X-ray properties you can Xray emission. And then X-ray fluorescence, the X radiation falls on the sample, but the radiation emitted has a different wavelength. Similarly, our electron spectroscopy, you take the electrons and then measure the wavelength of the different K lines, L lines of the different elements, that also you can take it to determine the concentrations on the surface. Now, X-ray absorption, like I was telling you, you take the basic radiation, total energy of the beam, pass it through the sample, loss of energy is determined just like molecular absorption. And electron spectro X-ray diffraction, it gives you the atoms at different positions of the crystal and the crystal structure can be determined. Now, the X-ray absorption and emission spectra are quite simple, but because they consist of very few lines, K alpha, K beta, L alpha and L beta. So, X-ray emission spectrum of an element may be obtained by using the sample itself as the target element. And this approach is not really very convenient for all types of samples, because sometimes you may have a liquid sample, then it is not possible to fit it onto the position of the target directly. So, sometimes you may have a powder, that is also not easy unless you have a metal which you can paste it and focus the incoming electronic beam onto the element. Now, instead what we can do is we can excite the we can achieve the same excitation by irradiating the sample with a beam of X-rays from an X-ray tube or a radioactive source, and in this method all the elements in the sample are excited by the absorption of the primary beam, which emit their own characteristic X-rays as usual, fluorescence, X-ray fluorescence. Now, therefore, the X-ray fluorescence is a powerful tool for the qualitative analysis, that is pass fail test. Suppose you are producing a metal in a foundry and then you would like to add some of the alloying elements and you would like to determine the concentration of the alloying element within a particular level. All you got to do is let the furnace run, let the metal melt, take a small amount of the melt and take it to X-ray fluorescence, just take the spectrum. If it shows you the X-ray fluorescence which is pre-calibrated to the known concentration, then you have a pass fail test ready. Very quick method and very easy to control. So, most of the high tech foundries have this kind of X-ray fluorescence lab attached to the foundry itself, where they can control the composition of the metal. So, XRF is also a non-destructive technique because the material does not get destroyed. So, unlike other elemental techniques where we have to either dissolve the sample and then extract, and the original nature of the sample is lost. So, there are two types of X-ray fluorescence spectrometers. One is you can monitor the wavelength of the dispersed X-rays, or you can monitor the energy of the X-rays. So, important instrument components of a source X-ray, XRF, I have shown here. Here is an X-ray source, that is X-rays will fall on the sample, and then you have a detector followed by electronics and the computer. Then you can have another kind of arrangement where X-ray source will fall on the sample and then you have an analyzing crystal through, and the emitted X-rays are focused using metal thin metal films here, the 1 and 2, and then onto the analyzing crystal. From there again it is focused onto the detector, followed by its electronics and the computer to control the measurement. So, what are the different types of sources for X-rays? How do you generate the X-rays? And other instrumental aspects are same, whether it is Auger, whether it is SCA, whether it is X-ray absorption, emission, etc. So, we are going to study the basic instrumentation for X-rays now, and then we will go on to the analysis of X-ray fluorescence technique. Other techniques we are not studying right now. So, what does an X-ray tube has? Basically, an X-ray tube is a high vacuum sealed off tube containing a heated filament from which we let the electrons flow, and these electrons need to be accelerated using high potential, that is the requirement. So, the cathode can be a filament which can simply generate the electrons when it is heated, and the anode has to be a 5 by 10 mm heavy block of copper with a metal target plated or embedded on its surface, and the target materials could be any element like tungsten, chromium, copper, molybdenum, rhodium, scandium, silver, iron, cobalt, any element what you would like to study. So, you need two circuits, one is for controlling the heating of the filament and another to accelerate the electrons and make them go and hit the cathode. So, the heater anode, not the cathode, but it is the anode. So, the heater circuit controls the intensity of the emitted X-rays and the accelerating voltage determines the energy of the electrons or the wavelength. So, both and current and the voltage must be stable up to 0.1% accuracy, that is very important. Otherwise, the energy of the X-rays will not be constant and most of the measurements will go awry. So, X-ray generation by this method is basically an inefficient process and much energy is wasted as heat. So, cooling of the anodes is a must. So, you will have to have a water cooling system to cool the anode, and modern equipments what they do is they use highly sensitive transducers and hence they avoid cooling. Cooling is not necessary. Sometimes in such cases the X-ray beam that is generated in the source has to come out and fall onto the sample. So, we use a beryllium window or aluminum window or palladium films for this purpose, because you need to take out the X radiation from the source out of the tube and focus them onto the sample. So, I am going to show you an X-ray tube here. The cooling water, there is a cooling water in and cooling water out. So, the whole thing is cooled continuously during operation, and then we have a metal target anode here, and this is the filament, tungsten filament is we have used, and this is a focusing cup. Whatever are the electrons generated will be focused onto the target anode, and then you have a circuit here for accelerating the voltage, another for heating the element. This is for the heating, this is for the another circuit for the high voltage, and we have a beryllium window here through which X-rays are coming out. You can have beryllium or any other element. So, the current is basically regulated by monitoring the X-ray tube DC current and controlling the filament voltage. When the full wave is rectified, the voltage reaches its peak value 120 times per second and persists for only a small fraction of the time. That means, 120 times per second you are going to get X-rays in per minute, which is available to you. When the tube is operated at 50 kV, the gain is approximately two-fold for elements up to atomic number 35, and it increases to four-fold at barium. That is, you keep on increasing the atomic number up to 35, increase is two-fold, and then you take some other metal and reach up to other metals one by one, and when you reach the atomic number 56, that is barium, the energy reaching the detector will be four-fold compared to bromine. So, normally X-ray tubes are operated between 50 to 60 kV source, power source, but nowadays you can operate tubes with 100 kV also. For these are for high end elements. So, this is this I have shown you. Another way of producing X-rays is to use radioactive substances such as hydrogen tritium and iron, cobalt, cadmium 109, 48, 109 top numbers refer to the atomic weight. here I have written cadmium 10948, and then iodine is 12553. Like that, there are number of elements which are radioactive, but they generate X-rays. So, some elements produce simple line spectra, others produce a continuum. A given isotope will be suitable for exciting a number of elements. For example, a source giving X-ray in 0.3 to 0.47 angstroms is suitable for XRF studies for all elements up to silver. The sensitivity improves as the wavelength of the source line approaches the absorption edge. Now, in some applications, X-ray tube with tungsten target is used to excite K alpha and K beta lines of molybdenum. The resulting fluorescence spectrum would also contain only line spectrum, which can be used for the excitation of the analyte. So, after you have X-rays generated from an X-ray tube or a radioactive source and they come out, you need to filter unwanted X-rays. So, just like in other electromagnetic radiations, when how you want to remove the unwanted radiations, here also you need to use filters. So, in some applications narrow ranges are required, wavelength ranges are required, you do not need all kinds of X-rays. So, you do not need continuum also. So, both filters and monochromators are used for this purpose. So, zirconium filters are very ideal for this, and they can be used in films of about 0.01 centimeter thickness to isolate K alpha line also. They not only eliminate the continuum, but they eliminate K alpha line also, and you can see here in this figure, you can see in this figure that wavelength is plotted against absorption of emission. So, here I have a filter in this range that is between 0.6 and 0.8, approximately around 0.7. There is a continuum X-ray coming like this, and then there is K alpha line and then K beta line, and you need to use only K beta line emitted by the molybdenum target, that is this line, but you do not need the other part. So, what I do is I use a zirconium filter which will cut off all the radiation that is coming in this range, including the K alpha line. So, this is the job of the filter. So, what is available after using the filter is only the K line, K beta line. So, several other filters also are available, and basically thin strips of various metals, and you can choose their characteristic cutoff wavelength is different. For example, in this case it is around 0.65 or 0.7, but for some other elements it may be something else. So, depending upon your requirement you can choose the filter. Now, after choosing the filter, you also need, just like in UV visible spectrophotometry, monochromator systems. In X-ray monochromators, if you remember what I had taught you earlier, we had used we had defined an X-ray monochromator system containing a lens, a focusing lens, a slit and a prism and or a grating, and then again a refocusing slit, etc. This is known as monochromator system. So, similarly in X-rays also you need to have a monochromator system, and this consists of a pair of beam collimators, that is to make the beam parallel. One serves usually you can use two filters, one for as a slit, one to serve as a slit and the other serves as the dispersing element. So, the dispersing element is basically a single crystal mounted on a goniometer. What is a goniometer? A goniometer is a rotating table that permits the determination of the angle of theta, that is the angle at which the radiation falls on the crystal, and the crystal, and then it gets refracted, diffracted, fluorescent, etc. And this angle, you suppose your sample is on a rotating turntable, the radiation will fall like this, and then this angle can be varied from 0 to 90 and 180, followed by 360. So, all the 360 degrees you can vary the angle of incidence of the X-rays. So, the goniometer permits you this arrangement. It is nothing but a circular arrangement on which the electrons are coming, and this angle of incidence from where the angle is from where the X-ray is coming is can be varied precisely for determining the X-ray, and the detector has to be located at twice the angle. That is, if we use Bragg's law, n lambda is equal to 2 d sin theta. We have studied it earlier, but it is also coming further. That means, for every angle of theta that the X radiation falls on the sample, the detector has to be rotated to twice. Suppose your angle of incidence is 35 degrees, the detector has to rotate at 70 degrees. So, both the turntable as well as the detector have to be rotated exactly, one at half the speed, one another at twice the quantity of the theta. That is the between the crystal face and the collimated incident beam. So, Bragg's equation shows that for any given angular setting goniometer, only a few wavelengths are diffracted according to this equation. It is n lambda is equal to 2 d sin theta, which I have explained just now. And to produce the spectrum, again what you need, the exit beam also has to be collimated once again, and the detector must be mounted on the another second table that rotates at the twice the speed that I have told you. And modern X-ray monochromator systems have microprocessor controlled motors to drive the crystal, to rotate the crystal and the detector independent of each other without gear based mechanism. What is the problem with gear based mechanism? If you use a gear based mechanism to rotate something, gears can wear out. So, subsequently, after you use it for some time, the gears can wear out and the angle, the precision of the angle would not be there at all. So, gearless mechanical systems are more comfortable in this kind of arrangements. So, they can scan rapidly. If they are gearless, you can scan the whole 360 degrees in a very short time, because there are no gears involved. So, you can scan them at the rate of 240 degrees per minute. So, this is the advantage of gearless this thing. Here I am showing you a monochromator system for X-ray. That is, what I have here is an X-ray tube on this side, and the sample is here. X-ray from the X-ray tube, they fall on the fluorescence beam, and then it the rotating table detector is located here, and then sample position for X-ray absorption analysis etc. are there. X-ray sources, the crystal is here and the transducer is here. So, The sample X-ray comes here, falls on there is a collimator, one for the incoming, one for the outgoing, and crystal is here, and then detector mounts are put here, etc., all around the turntable. And for this degree, theta degree change in the X-ray angle, the goniometer has to turn twice. This turntable has to turn twice the angle of incidence. So, this is what we have been talking about. The collimators basically consist of a series of closely spaced metal plates that absorb all the radiations except the parallel beams, because the radiations scattered in other directions have no meaning for the chemical analysis. What is coming out through a thin film of radiation which is parallel, that only is useful. So, X radiation longer than 2 angstroms is absorbed by the atmospheric gases. This is another important concept you should understand. That means, longer than any X radiation longer than 2 angstroms should not be open to atmospheric gases. That means, you need to have a vacuum system if longer wavelengths are required. So, the sample compartment must be flushed with either helium or some other gas which does not absorb X-rays, or it must be evacuated. So, with flat crystals, up to 99% of the X radiation is divergent, which is absorbed by the collimator wastage 99%. This loss can be minimized by about 10% using a curved crystal surface. Suppose your crystal is not exactly a 90 degree this thing, you can machine it and shape it into a curved surface like this, then the loss can be minimized by about 10%. So, and this divergent beam, the curved surface also will help in accomplishing the further focusing. It will have any curved surface, if X-ray falls on that, it will act like a concave mirror or convex mirror, where it will try to focus the divergent beam from the source on to the exit collimator. So, here there are some diffracting crystal properties like topaz, lithium fluoride, sodium chloride, and then ethylene diamine tartrate, D-tartrate, and ammonium dihydrogen phosphate, etc. Their lattice spacings are given here 1.356, 2.014, etc. The wavelength ranges are given here. The dispersion is approximately in the fourth column at lambda max and at lambda minimum. So, if you want to get X-rays of between 2 and between 2.67 angstroms and 0.24, you should go for topaz. This is how the table can be utilized. Suppose you want 8.6 between 8 and 0.7 and 8 angstrom unit X-rays, then you should go to this table and look which of the material gives you the radiation corresponding to between 0.77 and 8.67, that corresponds to ED/dt. So, depending upon the angle wavelength, you should be able to choose the wavelength material crystal for X-ray collection. So, the useful wavelength range for a crystal is determined by its lattice spacing d, that is n lambda is equal to 2 d sin theta, that is what we mean by d. D corresponds to the lattice spacing the spacing in between the two elements, two atoms rather, and this happens the detector problems are more if the angle of incidence is less than 10 degrees. So, if the angle of sometimes the angle may be 35 degrees, 90 degrees, 120 degrees like that. Below if it is almost parallel approximately 10-degree angle, the detector will have problems in collecting the X-rays emanating from the crystal. Same thing happens when the angle approaches 180 degrees. So, less between 170 and 180, detector will have problem in collecting the radiations quantitatively. Between 0 and 10, as you start from one end to the other end, this is 0 and then slowly you will increase. First 10 degrees there is a problem of collection, then it improves detection collection, it reaches 90 and then slowly when it comes to 170 degrees again it is almost parallel. Between 170 and 180 again the detection problem exists. So, what we do is in between we try to work between only up to 160 degrees in X-ray work. So, crystals with large spacings offer better d-spacing, lattice spacing offer better control over the scatter control, but it results in lower dispersion also. This is a consequence of the X-ray Bragg's law diffraction this thing. If you differentiate Bragg's equation, what we get is d theta by lambda is equal to n over 2 d sin theta, and this 2 d comes in the denominator. Therefore, d theta by d lambda, this dispersion is the measure of the dispersion that is inversely proportional to d. On the one hand, when the d is large, we get a better dispersion, better collection, but because it is a measure of dispersion which is inversely proportional, you get other problems. So, low dispersion prohibits the use of shorter wavelengths. Hence, topaz or lithium fluoride must be substituted in most of the X-ray fluorescence work. So, X-ray, now we move on to, we have discussed so far about production of X-rays, we have discussed so far about the use of filters, we have discussed about the monochromator systems and how the sample has to be mounted and how the angles and goniometer have to be arranged. Now, let us discuss about the detectors. In the X-ray, detectors are usually operated as photon counters. In this mode, individual pulses of the charges are produced as quanta of radiation, which are absorbed by the transducer. Basically, X-ray is nothing but the X radiation has to come and hit a particular sensitive transducer, and amount of energy has to be released, quanta of energy that has to be counted. So, this requires rapid response time because X-rays are very fast, electrons are also very fast moving, X-rays also are very fast, and therefore, the transducer as well as the signal processor have to work in within microseconds. The moment it hits, within a few microseconds, the whole measurement and counting and all other related systems must be completed before another photon comes and hits the detector. So, this technique is useful for low intensity X-ray beams, because in high intensity X-ray beams there is not much time for each photon to be counted individually. So, when X-rays pass through an inert gas such as argon, xenon or krypton, a large number of positive ions are also generated, electrons are there, and then X-ray quantum is there. Therefore, the conductivity of the gases increases because the positive ions and the electrons are generated, argon cation and electrons. So, electron is very lightweight and argon cation is a more higher weight sample. So, it moves slowly, but the electrons will move very fast. So, the conductivity of the gases increases from this phenomenon. Ionization chambers we use, proportional counters we use, and gauger counters are used to measure this enhanced current. So, basically X-ray measurement means you have to measure the current that is produced subsequently. So, a typical gas filled transducer I am showing here. You can see here I have a gas filled material and anode is here, X-rays are falling and this is a beryllium window, parallel X-ray beam is falling here and unabsorbed X-rays are going out, and I need a metal tube. Here argon is filled and the window, another window is here, and the amount of radiation that is generated has to, there is a cathode here, there is anode here. So, the electrons cations will move towards this side and electrons will move towards the cathode, and the amount of current generated is to be amplified and used. So, this is how a gas filled detector works, and if you look at the amplification of the detector signals, you will see three regions. Here in this figure I am showing you one first bottom curve corresponds to 0.5 angstrom X-rays, and the top curve, this one, corresponds to 0.6 angstrom X-rays. So, if you look at the applied voltage, it varies from 0 to 1600 and number of electrons per photon have been plotted here. So, there are, you can see that there are three regions, one is V1 and V2 and V3 and V4, another is V5 and V6. So, three regions, different distinct regions can be identified in these systems. So, the first region shows the number of electrons reaching the anode, which is fairly constant for each photon. That means, the amount of energy is constant and it can be detected very easily. In the second region, that is V3, V4, in this region there is, you can see that the slope has changed and it has increased enormously in this range current. So, this region number of electrons released increase rapidly with applied voltage, and here the secondary ion pair production occurs due to the collisions between the accelerated electrons and gas molecules. Therefore, under these conditions amplification of the current occurs. So, the third region, that is V5, V6, again here there is a sort of saturation occurring, and the amplification is enormous, but the current is independent of the type and energy of the incoming radiation. The current is actually governed by the geometry of and gas pressure of the tube. This region is known as Geiger region. So, scintillation counters are another types of detectors, where we use a sodium iodide crystal containing 0.2% thallium iodide shaped in the form of a cylinder and in about 3 to 4 inch in dimension. So, one surface is plane and which faces the cathode of a PMT. As the incoming radiation passes through the crystal, its energy is lost to the scintillator, which is subsequently released in the form of photons of fluorescence radiation. So, the flashes of light produced are transmitted to the photocathode, which in turn produce an electrical pulse that can be amplified. So, in X-ray now we come to, these are the, so far what I have covered is the basic instrumentation for X-ray fluorescence for all X-rays. Now, we come to X-ray fluorescence. As I have explained to you earlier, we have wavelength dispersive X-ray, WD XRF, and energy dispersive. So, In both these systems, a radioactive source is collimated and dispersed into its component wavelengths. Both single channel and multi channel detection systems are possible. In what do we mean by single channel and double channel? Multi channel. In single channel elements, you are going to determine only one element, and in multi channel elements, you are going to determine number of elements simultaneously. So, the angles for each element have to be set specific for each element. So, the counting progresses until sufficient counts are obtained for precise measurements. The instruments can be automated to cover the entire 360 range. In such instruments, the movement of the crystal and the detector are synchronized. Such instruments usually cost around 25 lakhs of rupees, and in multi-channel instruments they are costlier. They cost approximately $150,000 and they are useful for the determination of up to 24 elements simultaneously. In these instruments, individual channels for each crystal, for each element are arranged radially around the X-ray tube and sample holder. The crystals for most of the channels are fixed at an appropriate angle for a given analyte. That means, if you want to determine chromium, you need one crystal and then one detector system, one channel, one amplifier, one pulse height detector, etc. And similarly, every element to be determined, there have to be so many different channels, and the analysis, the whole analysis would be completed within a few seconds or maximum a couple of minutes. So, in energy dispersive X-ray fluorescence, it has a polychromatic source. That means, an X-ray source or a radioactive material, a sample holder, a semiconductor detector and various electronic components. So, the analytical methodology is also very simple here. That is, there are no moving parts and no collimators or crystal diffractors. Therefore, the entire energy reaching the detector is approximately 100 times more than wavelength dispersive XRF instruments. So, low power energy X-ray tubes or weaker radioactive materials can be used as radiation sources, which are cost effective and more safer to use. Why I am telling you all this is, when you want to buy an instrument for your laboratory, you should know what are the different sources, what are the detectors, what are their costs, what are the collimators, what are the lines, etc. So, this information would be very useful when you want to go for an instrument of this type. So, here you can see the amplifier is there, sample is here, then helium cooling, and then beryllium window is here. This is the beryllium window, and then a detector, and then amplifier and multi-channel pulse height analyzer. So, fluorescence radiation keeps on coming like this. For each element, you will have different kinds of the crystals and the detectors. So, this is the Martian rover detector, Mars mission rover detector. Here you can see that X-ray detectors are all located around these 6 head APXS. This is the front view, and alpha source is there, contact ring is there, and then door, etc. Other things are all set here. This we had discussed in the first lecture also. So, the sensor head in the rover contains curium 244 source that emits X-rays and 5.81 MeV alpha particles. So, the multiple element determination can be obtained by particle induced X-ray emission method. So, the X-ray detector is a new room temperature type that exhibits very low noise. If the detector is operating at very high temperature, that means it is going for higher noise. That means the detection limit will be lower. So, this is the XRF determination of the Martian rocks, you can see that in a single analysis sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, titanium, calcium, manganese, iron, nickel, copper, zinc, approximately about 24 elements have been determined in the Marshall rocks, and they have been determined. In multi-channel X-ray, all emitted X-ray lines are measured simultaneously. So, improved sensitivity is obtained and improved signal to noise ratio is obtained. This is known as Felgate advantage. We will discuss about the Felgate advantage while we are talking about infrared radiation also. So, improved resolution at shorter wavelengths is possible. Nowadays, a benchtop EDXRF is available for the routine determination of up to 12 elements ranging from sodium to uranium. The fluorescent signal is obtained by using appropriate filters, and that strikes the bottom of the rotating table where the detector is located, and the rhodium anode X-ray tube, 5 programmable filters, helium purge system is available, a 12 positive sample changer is there, and a spinner to rotate. So, this is the picture of a benchtop XRF model, where you can see the different samples, sample spinners, and then detector, filter wheel, X-ray tube, and sample turntable. So, the EDXRF basically plots the intensity of the CPS, and which can be quantified like this. The applications, analytical methodology, we will continue in the next class. There is very little to be said about the analytical methodology and other systems, analytical aspects, that we will discuss in the next class, and then continue on to atomic absorption spectrophotometry.